Well, in this video, let's do one example on one-dimensional steady state conduction heat transfer when we have heat generation in one of the layers. In this example, we have a thin silicon chip and an 8 mm thick aluminum substrate separated by a thick epoxy with a thickness of 0.02 millimeter. Chip and substrate are each 10 millimeter on a side. Their exposed surface are cooled by air with a known temperature of 25 degrees C and heat transfer coefficient of 100 watt per meter square Kelvin. Now the question is, if the chip dissipates 10 to the power of 4 watt per meter square under normal conditions, will it operate below a maximum allowable temperature of 85? So the best way to treat those problems is that let's go ahead and create a schematic drawing for this, which helps us to better understand the problem, and then we go and formulate it. So in this problem, we have a silicon chip, this layer, which is connected to an aluminum substrate underneath through an epoxy. So this is my silicon chip. Then inside it has electronic which generate heat. This is the epoxy. And underneath you have the aluminum substrate. So each layer are kind of shown like this. The thickness is given, and we know we have heat generation inside the chip. So let me go ahead and kind of show the Q dot, the volumetric heat generation, and the amount of Q dot is 10 to the power of 4, 10,000 watts for every meter square. And on the sides, we have convection on top and bottom of the setup, where temperature of the air is 25 and heat transfer coefficient is 100. Same thing at the bottom, air temperature 25 and heat transfer coefficient 100 watt per meter square Kelvin. Now let's go ahead and show our thermal resistance network for this particular case, and that's going to help us to better model this problem. So I'm going to first show my temperature points. Let's assume this is the temperature of the fluid on top, and here we have a temperature of the fluid on the other side. I have one resistance going all the way to the chip temperature. Let's call this chip temperature, or T sub C. Same thing here, from aluminum to the air underneath. I have a convection resistance, and as you remember, convection resistance, you can show it with 1 over HA, or 1 over H if you're dropping the A, okay? So let me show the full form, 1 over HA, and here 1 over HA. And by the way, because H values are the same, and of course A values are the same, so you don't need to call it H1 or H2. So that one was T sub C, which is the chip temperature. Now, going from chip, now on the other side of the chip, you are in epoxy, where I'm gonna go from a contact resistance. Contact resistance is when you have a perfect contact with another substrate. Also, in theory, in reality, there are micro gaps that still exist between them, which either you fill it with epoxy, which fill it with air gap, sandwich it with layers. Still, you have some resistance between the two substrate because of the third material you're sandwiching in between. Hence, we are defining an R double prime contact resistance, which we're going to use a table to find that value. That's just additional resistance because in reality, you cannot have 100% contact between the two silicon and aluminum between any two substrates. Okay, I'm going to talk more about R double prime, and also through the aluminum substrate we have one more resistance. And what is that? That's nothing but thickness of the aluminum. Let's call it L, which is, this is my L, divided by thermal conductivity times A. So this is my thermal resistance model. Also, I'm going to show you where heat is added. So, I'm sorry. Let me erase this part. So heat is added here, which is Q dot times area. Because Q dot has a unit of watt per meter square, and you multiply by that area to get the amount of Q in. By the way, you can drop all the A's because A's are constant for all of those. A's is nothing but the width of the substrate times, let's say, unit length into the board, so into the screen. So really, in this case, they're going to be constant and the same. So this is what we have so far. Let's go ahead and start solving this. To solve this, we know that, so this is air. We know that from energy balance, amount of heat generated inside the silicon chip, which is equal to Q dot times area, okay? That amount is going to be dissipated either from top. Let me show you. So whatever heat generated inside the chip, let me show it with this, either going on top or remaining going to the air in the bottom side. Let's call the top one Q1, the bottom one Q2. So whatever heat is generated inside the silicon chip, which is equal to Q dot heat generation rate times the area, is they're going through Q1 and remaining going through Q2. Okay, everybody okay with this? Because remember, it's a steady state. SSS stands for a steady state. It means that you're not accumulating heat in any layer. We are not sinking heat in any layer. So heat generated in a steady state should leave the silicon chip. That's why we can continue working and temperature hopefully remains at set point. If this is the case, well, at this point, I'm going to show it with Q total. If this is the case, I'm going to divide all sides by area and say the heat flux generated in a silicon chip is equal to heat flux going through top layer plus heat flux going through the bottom layer. By the way, heat flux is nothing but heat rate divided by area. And if you look at the unit of heat flux is watt per meter square. Unit of Q is watt, and unit of area is meter square. So it makes sense, right? Heat flux is nothing but heat divided by area. So we keep going down. So let's call it the heat flux of the chip. Heat flux of the chip, I can rewrite it as the amount of heat going upward is nothing but temperature difference between these 2 points, T infinity and chip temperature divided by resistance in between, right? That's the heat going to the top, and also heat, this is Q2. So instead of Q1, I am willing to write delta T, chip temperature minus T infinity divided by the resistance I have in between, which is nothing but this convection resistance, which is 1 over H. And remember, since I'm showing heat flux, I'm going to drop the areas from the resistance. Instead of 1 over HA, I'm putting it 1 over H. And how about Q2? So this is, that was just the Q1 term. Now I'm going to write about the heat flux going through the bottom direction with Q double prime 2. Same thing. You have a delta T, Tc minus T infinity, and the resistance between them, which is R double prime, L over Ka, and you have one convection resistance on 1 over HA as well. Again, remember, we're dropping those areas. So here I have delta T, Tc minus T infinity. What resistance I have? Contact resistance plus resistance by the aluminum bar thickness, which is L over K. Again, I'm dropping the A's here, plus resistance by convection 1 over H. Okay, so that kind of represents the Q double prime 2. And if you, I hope, I'm assuming everybody remembering that in conduction, we can say heat is temperature difference divided by total resistance, right? Similar to in electric circuits, current is equal to change in voltage divided by total resistance. So our voltage changes is our temperature changes in this analogy, and current represents the heat going through. So now we need to find some values such as thermal conductivity, R double prime, and so let's quickly look at this together. So we are looking for chip temperature to make sure it's below 85 degrees C or not. We have the T infinity, we're looking for Tc. We are having 1 over H. L is known, but K, we need to find it from tables. R double prime for contact, we need to find it from tables. And we do know about the heat flux generated because it's given as a volumetric heat generation of 10 to the power of 4. So we kind of know this as well. So if I know the properties of the material K, and if I know the contact resistance, I should be able to find it. So let's go ahead and try to find those. So let's just start with K values for the pure aluminum. How we can find it? You need to go to tables to find it. Let's go here. I have a table ready for us to, so this is a table A1 of the Incorporated textbook that we're referring to in this case. Let's say at temperature of, so this is my aluminum in a pure form. At 300 Kelvin, you had 237. At 400 Kelvin, you have 240. And if we're going to report it at 350, this is going to be the average of 237 and 240. So going back to our problem, do we have any temperature values? So let's go ahead, say at 350K, the K value for aluminum is 239 watt per meter Kelvin. Again, we don't have a certain temperature, that's why we are saying at roughly 350K. Again, you can be close to this, even not necessarily this, but as long as you write it down, your K where you find it, and it's a meaningful guess for the temperature, approach is correct. And we can always come back. If we solve the problem and we see that temperature we find for the chip is hugely different than what we assume, we can always adjust it and redo the problem. Also, we need the contact resistance value, correct? So let's look at the contact resistance. We have a table in the textbook that kind of summarize the thermal resistance of representative solid-solid interface. So if you have two solids, and also it tells you what bonding material you use, it gives you an R value. And remember, the R value, R double prime contact, you have to multiply by 10 to the power of 4, and the unit is already meter square Kelvin watt. So I can, yeah, meter square Kelvin watt. So in this case, we have a silicon chip and aluminum are solid to solid. And by the way, we have a 0.02 millimeter epoxy. So that's a perfect example for us. Perfect match for our example. So in this case, I can pick anything from 0.2 to 0.9. And to be more conservative, we can take the max resistance, assuming it's the worst case. So my resistance would be 0.9 times 10 to negative 4 meters square Kelvin over watt, correct? So my contact resistance, R double prime thermal contact based on that table is 0.9 times 10 to the power of negative 4. That's meter square, let me see, meter square Kelvin over watt. Okay, I am going to quickly go back here. And say, if I'm going to be consistent with everything dividing by area, I'm going to divide this by area, but at the end, those area will cancel out, just to be consistent with this. So now that I have all my terms, let's go ahead and formulate what we have. So again, I'm looking for TC. I have everything else in this equation. How about I separate TCs and isolate it, put it on the left-hand side, everything on the right-hand side. If you do this, from this equation, you will have chip temperature, or TC, is equal to T infinity plus heat flux generated inside the chip times H plus 1 over contact resistance that we found from the table, L over K, and 1 over H. Okay, just we did some rearrangement of this equation. And again, we're looking for TC. So TC is, T infinity is 25 degrees C plus, what is the heat flux generated in the chip? 10 to the power of 4 times H was 100 watt per meter square Kelvin. 1 divided by thermal resistance by the contact. We found it to be 0.9 times 10 to negative 4. And L over K, if you divide the thickness by the material property we found, is going to be 0.33. By the way, I'm gonna multiply everything to 10 to negative 4. And 1 over H, which is 1 over 100, would be, in the form of 10 to negative 4, would be 100. And if you do this, your answer will be 25 plus 50.3 equal to 75.3 degrees C. As you can see, it's less than question temperature, which is 85 degrees C. So our chip is being cooled fine, just for the normal condition based on this. So that's our answer. By the way, we can do a double check on the unit. What is the unit of this term? C. What is the unit of this term? Well, the unit of 10 to the 4, because that's the power, right, is watt per meter square. And the unit of this bracket, which is kind of summation of resistance we have, is meter square Kelvin over watt. Now we can go ahead and kind of cancel out to double check our work. Let's see, meter square cancel out each other, watt to watt cancel out each other. So I have degree C and Kelvin, which again, in terms of differences, they are same unit. So we are fine in terms of unit. Exactly, I have TC in terms of temperature as well. So this is our final answer. Thank you.